All right, so here's our first example for gravitation. So we have determined the force of gravity between you and a friend 5 meters apart, and we want to use 70 kilograms for both masses, and then big G, of course, is 6.67 times 10 to the negative 11th. So we know that the force of gravity, Newton's universal law of gravitation, we have big G times mass 1 times mass 2 divided by r squared. So force between the two is big G 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared, times mass 1, 70 kilograms, times mass 2, 70 kilograms, divided by the distance between you and your friend, 5 meters, and then we're going to square that. So we get times 70 times 70, and then I'm dividing by 25. We get a force of about 1.3 times 10 to the negative 8 newtons. So obviously this force is super, super small, right? And that's the reason we have to have that big G. And Newton, knew that there was a really, really small number in his equation, because if this force was big, if we didn't have that really small gravitational constant, then you would see and feel an effect on every single mass around you. So obviously we have to have that universal gravitation constant, that really small number, in order to make this force the correct size. Of course, when we have bigger masses like the sun, the moon, the earth, things like that, then we will actually feel this force, which is why we're able to stay on the earth. So now we're going to determine the force of gravity between you and the Earth. Again, we're going to use 70 kilograms for your mass. The mass of the Earth is given. It's 5.98 times 10 to the 24th kilograms. And then the radius of the Earth is also given, 6.37 times 10 to the 6 meters. Of course, when you're standing on the Earth, we're just going to assume that's you standing on the Earth. Our R is going to be from the middle of the Earth to you, which in this case is the radius of the Earth. So the R term in the force of gravity equation is going to be the radius of the Earth in this case. So we get force is equal to, again, G, M, M1 and M2 over R squared. So force is equal to 6.67 times 10 to the negative 11th times your mass, 70 kilograms, times the mass of the Earth, 5.98 times 10 to the 24th kilograms, divided by the radius of the Earth, 6.37 times 10 to the 6 meters, and then we're going to square that. So we get 6.67 times 10 to the negative 11th times 70 times 5.98 times 10 to the 24th. So the whole top, the numerator, I got 2.792 times 10 to the 16th, and I'm going to divide by 6.37 times 10 to the 6, squaring that. And I end up getting a force of 688.09. So about 688 newtons. Now, if you didn't get this, then show me what you're doing on your calculator, because a lot of these are just a calculator issue, especially when we start with the denominator here with a radius. If we are adding together like the radius of a planet and then say an orbital height or something like that, if you don't put parentheses correctly into your calculator, then you will end up getting the wrong answer. So if you're not getting the answers that I'm getting in these videos, then please let me know, show me what you're doing on your calculator, and we can figure it out together, okay? Now, this is 688 newtons. Now, of course, we're talking about our force of gravity, which in other words, we can say our weight on the Earth, right? So the quick way to do this, of course, is force is equal to mass times the acceleration of gravity. Mass in this case, your mass, we're saying is 70 kilograms. Acceleration of gravity on Earth is 9.8 meters per second squared. We end up getting 70 times 9.8, which is 686 newtons. So you can see that these two numbers are very, very similar. They are a little bit different because that acceleration of gravity, 9.8 meters per second squared, the one that we use here, it is a rounded number. So They're a little bit different, but this is where we actually can get the acceleration of gravity of a planet. And if you set these two things equal to each other, so I know force of gravity, of course, is equal to force of gravity. So mg is equal to g m1 m2 over r squared. M1 in this case was our mass, or your mass in this problem, 70 kilograms. So that mass cancels out on both sides, and then we get that the acceleration of gravity for any planet is going to be g, our gravitational constant, times the mass of the planet divided by r squared. All right, so you can actually find the acceleration of gravity using this equation as well.